Hi, I'm Dr. Eugenia Gold, and this is Science on the Street. This past summer, we were blessed with spectacular images of the past. Scientists around the world had waited with bated breath for these long-awaited snapshots. When they finally were released, many were led to tears. And why wouldn't they be emotional when it took teams of scientists literal decades to produce the tech that made these pictures possible and share them with the world? I am, of course, talking about the new deep space images from the James Webb Space Telescope. Today we'll talk about the history of space imaging and how the Webb telescope will improve our understanding of life, the universe, and everything. To really appreciate the Webb telescope, we need to go back to the 70s, when the Hubble telescope, originally called the Large Telescope, was first approved for construction. It took 13 years to build and launch and started producing images a month after its deployment. When Hubble began taking images, it became clear that something was wrong. A defect in the mirror, 1/50th the size of a human hair, created during manufacturing in a plant in Danbury, Connecticut, was to blame for the blurry pictures. We all know about Danbury. Hubble's defect was repaired by adding a lens in front of the sensor to bend the light further and focus the image properly, in the same way that glasses can address visual impairments. Thankfully, NASA had insurance on it, because imagine getting that medical bill in the mail. I'm pretty sure a space optometrist is out of network. According to NASA, Hubble has made more than 1 million observations over its lifetime and has provided key information about distant galaxies, atmospheric composition, black holes, and dark energy. To make its observations, Hubble is equipped with target locking sensors and 2 large mirrors that collect and focus the light from those targets onto its instruments. Hubble is more than just a large-scale camera, though. It has a variety of tools to sense visible light, near UV and near infrared wavelengths on either end of the visible spectrum, and instruments on board that read UV light, temperature, chemical composition, density, and motion. These tools allow scientists to understand what the atmosphere on a distant planet is made of without ever having to set foot there. They can understand the life cycles of stars from observing the remnants after their death, and it can sense black holes even when the dust surrounding them obscures them from the camera. With the momentum of these discoveries, it was clear that we needed to be able to see deeper into space. Scientists want to understand how the universe formed, and the farther we look into space, the further back in time we are observing. This is because light takes time to travel. Due to the vast distances involved in space, the light we are gathering and focusing into these images has taken millions of years to get to our telescopes. We are able to directly observe the past by taking these pictures, like time travelers. It's almost like pointing a camera at an adult and seeing them as a child. Enter the James Webb Space Telescope. It was launched in 2021 and orbits the Sun about 1.5 million kilometers away from Earth, as opposed to Hubble's 547 kilometers off the surface of our planet. It is equipped with a mirror almost 3 times the size of what Hubble has, which allows it to gather more light for finer resolution images. It has an infrared sensor, which is better at sensing through dust clouds and detecting further away objects due to how light stretches as the universe expands. In short, it can see farther and better than Hubble. If Hubble is looking back in time and taking photos of galaxies in their terrible twos, then Webb is able to image galaxies in their infancy. Aww. These tools have made it possible to improve on images taken by Hubble, like this one showing a distant galaxy cluster, where the Webb telescope was able to capture not only the galaxies present in the Hubble image, but also clearer pictures of the galaxies behind the ones in the image due to gravitational lensing. This is an effect where light from the galaxies in the further distance is bent around the closer galaxies due to their gravity, resulting in a distorted image, but allowing us to see what would otherwise be obscured. Webb also improved on this image of the cosmic cliffs in the Karina Nebula, an area of space where new stars are born. The cliff peaks in this image are around 7 light years high, which is orders of magnitude larger than our solar system is across. Besides pretty pictures, Webb is analyzing the physical and chemical composition of near and distant planets to understand the atmosphere, geologic history, and potential for life in other systems. It's only been 3 months since the Webb telescope started broadcasting images, and I can't wait to see what other wonders it finds. I have no doubt that they will continue to be out of this world. find out more, we spoke with Dr. Knicole Colón, Deputy Project Scientist for Exoplanet Science on the James Webb Space Telescope project. I'm sitting down with Dr. Knicole Colón from NASA's James Webb Space Telescope team. Welcome, Knicole.
Hi, thanks for having me.
Thanks for
Happy to
being
be here.
here.
Yeah.
Just to start out, what's your role on the James Webb Space Telescope team?
Sure. So my official title's kind of a mouthful. I'm formally the Deputy Project Scientist for Exoplanet Science. So to unpack all that, what that really means is I am kind of NASA's expert on extrasolar planets. And these are planets that orbit outside our solar system. And specifically, I'm the expert for the telescope in its plan to observe, analyze, study, learn about these exoplanets. So anything that we can do to improve the way the telescope looks at these distant exoplanets and how the data comes back from the telescope, anything we can do to improve the data analysis, that kind of thing, that's my role, is providing insight into how we can continue to make the telescope as basically as good as it can be for these observations.
Very cool. Have you been able to make observations of exoplanets yet? I know the telescope has only been really working for a few months.
Yes, actually, excitingly. Some of the first formal scientific discoveries to come out of the James Webb Space Telescope so far have been of exoplanets. So we've already produced data that's shown us the spectrum of an exoplanet atmosphere. So we're basically able to look at distant exoplanets and break down the starlight as it passes through the planet's atmosphere. And we can see, oh, there's something in the planet's atmosphere that's blocking starlight, essentially. And that something is a molecule, often like water or methane or carbon dioxide. But we haven't definitively seen carbon dioxide in an exoplanet atmosphere until about a month ago when JWST came along and took the observations and showed us. So we've been able to get the first definitive result out for that molecule with the telescope already in a couple months of observations.
That's amazing. So you're able to tell what kind of atmosphere a really distant planet has just by how light travels through it.
Yeah, basically either that or how it reflects off the atmosphere, because we can and do take direct images of exoplanets. So we can the technique before I didn't mention, but it's called transit. So transit technique. So we can basically watch the star as the planet passes in front of it, but we're not actually taking an image of the planet because it's so close to the star. All we're really seeing is the brightness of the star and how it's changing. But the brightness will change because the planet passes in front and blocks some of the starlight. But then it'll block additional starlight if there's something in the atmosphere causing like it's opaque, basically. So it's causing an additional decrease in starlight. And that's all about the transit technique. But then we can look at a different technique called direct imaging, where we can block the bright star and look for the faint planet next to it. And in that case, we can measure light from the planet, which is basically reflected starlight off the atmosphere. So we can do this, from really far away, and it's kind of crazy, but
it's amazing.
It's pretty awesome. Yeah.
Can you tell us a little bit about why the telescope is in orbit around the sun in a place that is basically not able to be serviced?
Yes. Yeah. So it's at this Lagrange point, as we say, and it's about 1 million miles away from Earth. But yeah, it's orbiting around the sun, kind of like in parallel to Earth. And why this is, really a few reasons, but one of the main ones is we needed the telescope to be really cold. And the Earth is pretty warm. So imagine if it's orbiting right around the Earth, you get a lot of warmth from the Earth that can warm up your telescope above where we wanted it to operate. And the reason we wanted such a cold telescope is because we want to go and look at infrared wavelengths of light. So this is going beyond the visible light that we can see, the rainbow of colors we can see every day. Beyond that, there's infrared light. So it's light that we can't see with human eyes, but we can design instruments to see that. But you basically have to have a cold telescope to be sensitive to that light. So in order to detect the light efficiently, let's say. So we needed the telescope to be as cold as possible to basically have super efficient observations at these infrared wavelengths. And so, yeah, operating a million miles away really helps us out so that we can get those sensitive measurements.
Gotcha. Yeah, that makes sense. So it's orbiting around the sun, but not close enough to the sun for the sun's own heat to be affecting the telescope.
Right. So yeah, the sun is definitely warm and it will heat up the side of the telescope, but that's why it has this massive sun shield. So it's like a big umbrella. So whatever the telescope's looking at, it's oriented such that that big it looks like aluminum sun shield, it's always facing the sun. So the sun will always be hitting that part, and then that cools off, those layers act like like an umbrella to keep the telescope cool and radiate the heat away from the telescope and not into the telescope instruments, so that we can make those teeny tiny measurements.
Of the images that have come out so far, and I know that one just came out that included Neptune, I want to say, which has been the most striking to you in terms of, what you can gather of data, of just beauty, or any of those?
Yeah, it's funny because I'm laughing because this telescope is basically designed to be, as we talked about, be sensitive to measurements, essentially of a distant universe, of all these really distant galaxies that formed kind of near the beginning of the universe, and to understand how they formed. And all that's well and good, but I do find the images of the solar system objects so just beautiful and informative. I mean, so far we've released images of Neptune just recently, and also even Mars and Jupiter, and all of them are really demonstrating that the telescope can do it all. It's observing everything from near to far, right? But B, when you look at those images, you'll actually still see galaxies in the background, because galaxies are just everywhere. So I love that every image of the solar system gets photobombed by galaxies, basically. And it's again showing the power of the telescope. Like, it's just that powerful that no matter where you look, you're going to see galaxies, no matter how short your we call it your exposure time is to take an image of Jupiter or Neptune or Mars, because these planets are really close compared to these galaxies, right? And so and the telescope's really big, so you don't need a lot of exposure time to take these images. But even in that short amount of time, you still see all these galaxies. So that's just kind of like a really fun thing about those that I love. But honestly, it is the detail that we're seeing. We're seeing the rings of these planets, of Jupiter that came out a few weeks ago, and Neptune. And these rings are just reminding us too that Saturn is not the only planet with rings, that all the major gas giant planets have rings in our solar system. And what we can get from that is understanding more about their composition, how they formed, even about the moons of these planets. Like all that we can get with the James Webb Space Telescope. So I love that, because it also, maybe I'm biased, but it ties into exoplanets, right? What can we learn about our solar system planets as much as possible to help us understand exoplanets? So, I don't study solar system planets, but I do love just the beauty and the knowledge we can get from these data that we're seeing come out in just, again, a couple months of operations.
Yeah, it's been an amazing summer to watch the buildup of anticipation of this telescope, and then these first images that are just incredible. Is there a place in the sky that we can point to and say, "Oh, the telescope is aimed that way right now"?
So, yeah, the funny thing is that people, when there's a will, there's a way. And people have made unofficial accounts, for example, on Twitter, social media, that can provide you with where the telescope is pointing and what it's looking at. And so that's honestly how I even found out it was looking at Mars, for example, on Twitter. And then a few days later, we put out the Mars image. So, like, it's pretty funny how that works, just things happen so quickly. But yeah, I mean, there is a whole institution that runs the operations for the telescope, the Space Telescope Science Institute in Baltimore, Maryland. And they basically create an observing schedule each week. And so we know where the telescope should be pointing. And then these, Twitter bots come along and scrape that information and put it to the right timing of when the observations are planned. Yeah. So there is a way to do that. It's usually, well, like I said, it's unofficial, but it's not, a NASA product. But you can still look and find what's being observed and say, hey, oh yeah, we're looking at some galaxy in that direction of the sky, right? Which is pretty fun.
So it seems like it sort of changes its observation target pretty rapidly. I had always assumed that it took a long time to get these images based on gathering light in space, but it seems like that's not actually the case. How long, on average, does it take to take one of these pictures?
Yeah, that's a great question because I don't think I really appreciated that either until we started operations where, the observing schedule, I mentioned it'll come up, or they plan it in weekly chunks. And there's just so much crammed in there because, well, with astronomy, I mean, you're working 24/7, like you can use your telescope 24/7, right? It's always facing away from the sun. So it's always able to look anywhere. It doesn't have day night time cycles. So you don't turn off at night, right? So you're observing around the clock, 24/7, 365 days a year. So you can jam pack the schedule and run through either observations of galaxies, stars, black holes, planets, exoplanets, all the things. And most of the time, again, this telescope is so powerful that you're only spending like a few hours on any given target. The exception, I would say, is for really some of the exoplanets, because when, as we mentioned earlier, when you want to observe an event when a planet has passed in front of its star and blocked light, that can take a few hours. And often we add extra data to buffer that around. So we kind of observe the star for a little while, and then the planet passes in front for a couple hours, and then we observe the star for a little while longer to have like a baseline. So I think the longest continuous observations tend to be exoplanets, and that can be still on order of just a few hours. But some of the observations for exoplanets already have been like even over 24 hours straight, essentially. So those are definitely the longer time spans. But yeah, for the most part, it's just rolling through targets like every couple hours, and it's kind of crazy. So there's a lot of data, but it's really exciting, how efficient it is.
So we can expect a lot more images to come in its lifetime.
Oh, absolutely. Yeah. I mean, we're still very much scraping the surface in every way, shape, or form. Like even all these images you see of the planets or galaxies or galaxy fields, right? With tons of galaxies, there's just constant data being taken. And that's the thing too, though. There are a lot of images, but there's a lot of spectra, like it talked about the rainbow of light, essentially, but it's an infrared rainbow that we can't see. But there's data being taken, and it's not always going to be pretty images, essentially. But that's okay, because these spectra are how we gain the most information about what different objects are made of, by understanding kind of the signatures that we see, and once you break down that light into components. So there's a lot of data, a lot of pretty images, but there's going to be a lot of these spectra too that basically look like bumps and wiggles, but they're pretty in their own right.
Yeah, they're important bumps and wiggles.
That's right. They're very important.
Not a lot. Some of the pictures that we've been seeing coming out of James Webb Space Telescope are of regions of space that Hubble has previously taken images of. Why is it important to take those pictures again with this new tech?
Mm-hmm. Well, Hubble's been incredible, and it's still going. That's the best part. It's still going. And the really nice thing about these two telescopes is that they are actually quite complementary. So we talked about with the James Webb Space Telescope, it's optimized for these infrared wavelength observations, so light we can't see. But what it can see is through dust and clouds. It can look for thermal emission from objects. It can look at warm exoplanets and take direct images of them. It can do all these things. With Hubble does a little bit of that in the infrared, but it really, actually, most of its observations are in the visible light, or also in the ultraviolet light, so higher energies, we say, than visible. So also light we can't see, but we talk about UV radiation from the sun, right? That's why we wear sunscreen. So it's that kind of light that Hubble can see. And so actually, when we look at things that Hubble has imaged already, some galaxy or a place where stars are forming, it sees one point of view essentially. And then the James Webb Space Telescope takes that view and it can go back to that same galaxy, that same place where stars are forming, and it provides a different view because now it's got a powerful view of looking at this thermal emission, these heat signatures, looking through clouds of gas and dust that maybe Hubble couldn't see through. So really they come together to provide us the full picture because we only see a part of the picture at any given wavelength of light. And so, the James Webb Space Telescope is also just generally more powerful, to be fair, because it is larger than the Hubble Space Telescope. Its mirror is larger, and it offers really just high resolution images too. And Hubble has and hopefully will continue to provide great data for as long as it can. But despite the differences in mirror size and resolution and all that, it's really the wavelength coverage that makes them complementary and why it makes sense to go revisit things that Hubble has seen.
You mentioned a little bit about this in your answer. What else is out there besides the stars and the exoplanets? What other kinds of, not structures, but I guess structures are you looking through or looking at in space?
Yeah, in a way, you name it, we can see it. So even kind of working our way outwards in our solar system, we can look at other planets outside of Earth. We cannot look at the sun or Mercury or Venus or the moon with JWST. We can't do that just because we have to stay pointed away from the sun. But we can look at everything in the outer solar system, as we say. And that also includes asteroids and comets. So we can study these distant, cold, small objects with the James Webb Space Telescope, which is exciting, and learn about their formation. Going beyond that, we can look around nearby stars to look for exoplanets. We can do that with taking direct images of them. We can look at regions where stars are forming or where stars are dying because stars have a finite lifetime, and so they're constantly evolving and shedding gas to then create new stars eventually. So we can look at that. And when stars, we say they die, they can leave behind different remnants also, and that includes black holes, for example. And so we can't see black holes directly, but we can see the effects the black hole has on its surrounding. So the James Webb Space Telescope is certainly looking at some of those, and that's all within our own galaxy. So our galaxy is made of billions of stars, and they form a massive structure, as you mentioned, right? Using that term, I think is a good term. It's a massive structure that's bound by gravity together. But there are billions of stars that make up our galaxy, but then there are billions of galaxies out there. So the James Webb Space Telescope can go beyond that and look at all the other galaxies too, and see out to some of the first ones that formed after the universe began, essentially, just the way that the light travels through the universe. It takes time to do that, and it hits our telescope. So we're basically like a time machine. So yeah, we can see essentially anything you can dream of. We can probably see it.
Incredible. I think that's one of the things about deep space imaging that is the hardest for people to wrap their minds around, is that not only that you can point it in a direction and almost image the beginning of the universe, but also that you can point it in any direction and still arrive at what might be near the beginning of the universe. I think that's it hurts my brain to think about.
I agree. Like there's not like one point in the sky that we point to and say, oh, that's where the universe was created, right? It's weird. I agree. Like it's hard to imagine it. And the universe, I mean, it's theorized, it's well accepted theory that it started with a big bang somehow, and then, but what's the origin point of that bang? There's not really one, because everything just kind of has been rapidly moving away, and like the universe is expanding from every given point, in any direction. Like everything is moving away from everything else, and it's very strange and to fathom that, right? And so that's a curious fact. But we have measurements that prove that is the case. Like every object is moving away from each other, essentially, on the grand scale of things. But also the way, light only travels so fast. So when we take our telescope, any telescope, we can open the shutter, if you will, and collect some light. But it took light a certain amount of time to get there. So with the James Webb Space Telescope, it's optimized also for these infrared observations, kind of for the very reason to see some of that first light, because the way the light travels through time and travels through space and all these things, it actually means that the distant galaxies that formed at the beginning of the universe are brighter in the infrared. It's a very weird thing to think about, but it's just the way the light, how it gets shifted through space and time, that they end up being really bright in the infrared. And so that means this telescope is even more optimized to see these distant galaxies.
Amazing. What kinds of data or images are you looking forward to gathering? I know that you already have a wealth of data to be analyzing. Is there anything specific that you're looking forward to?
I mean, definitely as we've seen so far, every image is beautiful, right? So I enjoy seeing each and everything, even if I'm an exoplanet person, right? But I love all the imagery, of the distant galaxies and these clouds, like when they show pillars of clouds of gas and dust that are, stars are forming there, and it's just incredible, and new planets could be forming there. So it's really a beautiful universe, right? So I love every image that we're able to collect of it. But of course, that said, I think, well, yeah, there is so much more data to come. We've only been observing a couple months now, and some of that data to come is pushing to smaller and smaller exoplanets, for example. So what we've seen so far has been focused on a lot of giant planets, like Jupiter-sized planets. But a lot of data to come will involves studying small planets like the size of Earth. So I'm really interested to see what we can learn about those planets that are Earth size, um, compared to our own Earth. I'm not sure what the answer is, but we'll see. So time will tell, basically. So that's one exciting avenue. And then just in general, JWST is also looking at some nearby stars to try to find planets that we haven't yet discovered. And I'm excited to see what we can find there. If we can find some planets around nearby stars. We have already, with some ground-based telescopes on Earth, and even Hubble has seen some of these too. But again, being optimized in this infrared wavelength actually really helps a lot to see some of these really faint planets around stars. So I'm really curious to see what we can discover, like literally discover in terms of planets that we didn't know existed yet, right?
Amazing. I look forward to that also, to hearing all the results. Is there anything that we didn't cover that you would like to talk about?
We mentioned a few times how we've just been operating for a few months, right? And everything has exceeded expectations, I'll say, right? Scientifically, well, operationally for one, like everything is just working incredibly well. And the one factor that goes with that is the lifetime of the mission. Like, we are learning so much already in just a few months of data. The nominal lifetime of the mission is 5 or 6 years, but we are thinking that we could probably get at least 20 years out of this. And if we're kind of getting all these new results right off the bat, in a way without even trying. I mean, we are trying, we're using the telescope correctly, but like, there's always things you learn along the way to even improve efficiency or, maximize operations and science output somehow, right? So as we continue to learn about the instruments and the telescope and move forward, I'm excited to see how we can just push even further. And I can only imagine the things we're going to learn in the next 20 years of data. So I think it's the beginning of a very long but exciting journey to see all the things we're going to learn. So yeah, I just want to, kind of emphasize that everything is awesome right now, but it's still only beginning. So like, I can't even imagine what else could come, but there's going to be so much to come.
Well, Knicole, thank you so much for being with us today.
Yeah, thank you for having me. It's been a lot of fun.
And join us next time on Science on the Street.